Hi chemists, happy Monday. We're actually going to talk about our last topic in the acids and bases unit today. Then we're going to do a few digital lab experiments later this week. And then we're going to move on to our last big topic, which is electrochemistry after that. So let's go ahead and get started.
All right, folks, take a look at this problem and see if you can answer this on your own. Good, so let's talk about this together. So in the first situation, we're mixing 10 milliliters of 1 molar HCl and 10 milliliters of sodium hydroxide. And in all of these situations, we're mixing HCl and NaOH. So we know that HCl is an acid and NaOH is a base. And so if we mix them together, they're going to react in a neutralization reaction, right, which is a special type of double replacement reaction. So the H plus and the Na will essentially swap places, right? We'll end up with NaCl and we'll end up with HOH, aka water. That's going to happen for all of these reactions. For the first reaction, we've got exactly equal amounts of HCl and NaOH. And so they're going to react together, and the only thing we're going to end up with is NaCl and H2O. And so the pH is going to be 7 because we've got a neutral solution. In scenario number 2, now we have different amounts. We have the same concentration, but we have different volumes, right? 10 milliliters of acid and only 5 milliliters of base. So some of the acid is going to react with some of the base, right, with all of the base, but the base is going to get used up, right? We're going to run out of base because we have more acid than we do base. And so once we run out of base, well, we'll have NaCl and we'll have water, but we'll also have a bunch of leftover acid that hasn't been reacted. So in scenario number 2, we're going to end up with a solution that's acidic. So we're going to have a pH that's less than 7. In scenario number 3, we have the same volume of acid and base, but now the concentrations are different, right? We have a 0.5 molar concentration of HCl and a 1 molar concentration of sodium hydroxide. So in this scenario, we have less acid than we do base because the acid has a lower concentration and the same volume. So we have fewer moles of acid and more moles of base. And so the acid is going to get used up and we're going to have leftover base. So this solution is going to end up with a basic pH. It's going to be basic. And so the pH will be greater than 7. And of course, you have to be careful to make the greater than sign different from the 7. So let's think about in general what has to happen in order to have a neutral solution, right? In order to get a neutral solution like number 1, you need to be adding equal amounts of HCl and NaOH. And when I say amounts, I don't mean volumes, right? In number 3, we had the same volume, but we had different concentrations, right? What matters is the actual number of molecules or moles of molecules that's added. So to be neutral, a solution must have the same, a solution must have equal concentrations of, or equal moles rather, of H plus and OH minus. Right, we need a solution that has equal moles of H plus and OH minus. All right, I brought in some lemonade that I pulled out of the refrigerator, and I want to know how acidic this lemonade is, right? So one thing that I could do is I could test the pH of the lemonade. So let me go ahead and do that. I'm going to pour a little bit out into my little espresso cup here. And then I'm going to test the pH using these pH strips. All right, so I've got my pH strip. I'm going to go ahead and dip this inside the lemonade, and then we'll compare it here. So it looks to me like we've got a pH of about 3, right? So based on having a pH of about 3, you could go ahead and calculate the amount or the concentration of H plus that's in my lemonade. All right, so we know the pH is 3. Whoops, my markers. There we go. We know the pH is 3, right? That's also equal to the negative log of the concentration of H plus, right? So that means -3 equals log of the concentration of H plus. So that means 10 to this power equals this concentration. So 10 to the negative 3 would be our concentration of H plus, aka 0.001 molar, right? Cool. Okay, but I'm not actually 100% sure that this had a pH of 3. It actually looks like maybe it might be closer to 2 than to 3, right? So when I measure the pH using pH strips, that doesn't give me a super accurate pH, right? So the pH is about 3, but maybe it's actually 2, right? Maybe the pH is actually 2. Well, if the pH is 2, let's think about what would happen to the concentration of the H plus of the acid, right? If we're off in our pH, right? If I accidentally misjudged the pH by 1, if I was off by 1, let's think about how far off my concentration would be. Right? We know that when pH goes down by 1, the concentration gets multiplied times 10. So if my pH was off by 1, right, the actual concentration of H plus would now be 10 to the negative 2, aka 0.01 molar, right? That's off by a factor of 10. That's a pretty big difference, right? That's saying, okay, well, if I was wrong, we've actually got 10 times as much acid as I thought there was. So using pH and using pH strips is not a very accurate way to figure out the concentration of an acid or a base, right? You can get a vague kind of general idea, right? I can tell that the pH of my lemonade is, or the concentration is somewhere in between 0.01 molar and 0.001 molar, but it doesn't give you a really, really clear idea. And so we need a more accurate way to figure out the concentrations of acids and bases. One of the best ways to do that is a method called titration. Right? Titration is a method for finding the concentration of an unknown acid or base by reacting it with an acid or base whose concentration you do know, right? If you want a solution whose concentration you do know, you could mix that solution yourself in lab, right? You could measure out exactly how much of the acid or the base you're going to put in, and you would know exactly, and measure out exactly how much water you're going to add, and then you would know the moles and the liters, so you could calculate the concentration exactly. But for something like lemonade, right, this wasn't made in a lab, it was made in, like, I don't know, a lemonade factory, and I don't think the people in the lemonade factory were, like, paying too much attention to the pH when they were making the lemonade. I think they just wanted to make something that tasted good, right? So if I want to know the concentration of my lemonade, I'll need to react it, right? So titration is a method for finding the concentration of an unknown acid or base by reacting it with and if it's an acid, you would react it with a base, and if it's a base, you would react it with an acid, right, of known concentration. So the reason titration works is that we know that for a neutral solution, you have to have equal moles of H plus and OH minus, right? And so if you know the concentration of what you're reacting, you can react it just enough to get the solution neutral. And then you know when the solution is neutral that the moles of H plus have to equal the moles of OH minus. The way we can tell if the solution is neutral is by using something called an indicator. Right, that's a substance that changes color when pH changes color. That changes color when pH changes. So cabbage juice is a nice example of an indicator. If you look at your reference table, there's a whole list of commonly used indicators in chemistry lab. All right, so if we look at table M in the reference table, that shows us common acid-base indicators. So these are substances that change color as the pH changes. So for example, right, methyl orange is red at a pH below 3.1 and yellow when the pH is above 4.4. right? And from this range, if you're in between 3.1 to 4.4, it's in the middle of turning from red to yellow, so it'd be an in-between color. It'll be orange, right? The indicator that's most commonly used in titration is phenolphthalein. That's this third one, which has a pretty dramatic change from colorless to pink, right around a pH of 8 or 9. So it's not actually perfectly changing at a pH of 7, but it turns out that this is close enough to give us very accurate results. So let's actually go ahead and watch a video, and we'll see how this is done in lab.
All right, we can tell that these folks are British because they're referring to the Erlenmeyer flask as a conical flask, which is a very British pronunciation. So we've got 25 milliliters of acid in this Erlenmeyer. We don't know the concentration of that acid. Right? And so the purpose behind this experiment is to figure out what that concentration actually is. All right, so now they're adding phenolphthalein. And as you can see, phenolphthalein is colorless in acid solutions, but it turns pink in basic solutions. So what we're going to do is we're going to add sodium hydroxide of known concentration into the acid. So we're adding NaOH until it reaches the 0 mark on the burette. Burettes are actually numbered backwards, so the 0 mark is up at the top. And you can see where the sodium hydroxide enters the solution, the indicator phenolphthalein briefly turns pink. Right? So phenolphthalein turns pink when it's in a solution that's basic. And so right when the drop drops in, that one little spot is basic. But then once you swirl it, the base gets reacted away by the acid. There's more acid than there is base as the base gets used up. And the solution goes back to being colorless. So what we're going to do is we're going to keep adding base right up until the solution goes from acidic to basic. Right? So we'll see that the solution turns pink right when it becomes basic. And at that instant when the solution is transitioning from acidic to basic, that's when the moles of acid are equal to the moles of base. Right? Technically, if the solution's pink, right, the moles of base is greater than the moles of acid, but only very, very, very slightly greater. And so when we know that the moles of H plus or the moles of acid is equal to the moles of OH minus, we can use that to calculate the concentration of the unknown acid. All right, so we're going to keep dripping in drops of base until the pink color stays. And you can see this is actually taking a while. It's kind of mesmerizing to watch. There we go. Okay, so right now, the pink color is staying. That tells us that the solution is overall basic, right? That's what that indicator phenolphthalein tells us. We're going to read the amount of sodium hydroxide that was added. So if you look at the burette right here, you'll notice that the burette is counting up as you go down, which is basically making it easier to measure out how much was added. So we started at 0 and we've counted down to, and we're in between 25 and 26. When you're reading a burette, it's always useful to just look for the 2 nearest numbers. But we're in between 25 and 26. We're going to be more than 25, but less than 26. Right. Each of these smaller markings, so there's 10 of them in between 25 and 26, they must be 0.1. Right, so it looks like we've added about 25.4, and really we should say 25.40 because we should give a guess digit beyond the markings on the burette. So the burette goes up by 0.1, so we're gonna go to the 0.01 decimal place, right? So 25.40 milliliters or centimeters cubed of sodium hydroxide is how much we had to add in order to exactly use up the HCl. So right when the solution turns pink, we stopped adding the base, and we're measuring how much base was added, and we know that we've added just enough base to exactly neutralize the acid. Good. And then if you were to do this in lab, we would always repeat the experiments to make sure that we're getting results that are within 0.2 milliliters of each other.
It's the idea behind the titration is that we're reacting the acid and the base, and the indicator changes color right when we're transitioning from an acidic pH to a basic pH. So essentially the indicator changes color right when we've added just enough base to neutralize the acid. That's not 100% true, right? Phenolphthalein actually changes color at a pH of around 8 or 9, not 7. But it turns out that that doesn't really matter too much. We can see why if we look at this graph. So this is what's called a titration curve. It's a graph of pH as a function of the amount of base that's been added to a solution of acid. So you can see the pH starts out really low, and then it increases as you're adding more and more base, right? The solution becomes more and more basic. And at a pH of 7 is right when the moles of acid equals the moles of base. That's called the equivalence point. And what you'll see is that the pH, it's not increasing in a line, right? pH curves pretty much always increase in this really characteristic sort of S-shaped curve, where right when you're near the equivalence point, the pH essentially skyrockets up. It has to do with this sort of weird log scale that we use to measure pH. So this is not just a linear trend, it's having this weird effect. And so the phenolphthalein actually changes color at a pH of around 8 or 9. Right, here's where the phenolphthalein is actually changing color, right? But the amount of base that's added is essentially the same, right? Essentially to go from even from a pH of 4 to about a pH of 10 takes about 1 drop, right? And so you'll see that color change when you add 1 drop from 4 to 10. And you'll see that very dramatic color change, and you'll know that you've exactly added the same moles of base as you have of acid. Right? Technically, you've added very, very slightly more base, but the amount you've added is about 1 drop, less than 1 drop more. And so essentially, we can say, okay, the moles of acid basically equals the moles of base. So good. So in a titration, we're saying that the moles of H plus is equal to the moles of OH minus, right? If we've got an acid that has more than 1 mole of H plus in the formula, or base that has more than 1 OH minus in the formula, this is what has to be equal in order to be neutral, right? The moles of H plus and the moles of OH minus. So from that, we can calculate our unknown concentration. So we know that we reacted 25.00 milliliters of H plus, and we reacted 25.40 milliliters of OH minus. And we also know that the concentration of the OH minus was 0.100 molar. We don't know what the concentration of the acid was. That's what we want to find out, right? But we know that the moles are equal. So we can go ahead and calculate the moles of OH minus and set that equal to the moles of H plus. Right. So remember that molarity is also moles per liter. Right. So we've got 0.1 moles per liter for our base. So we can calculate the moles of base by saying, okay, well, we reacted 25.4 milliliters. Let's convert that to liters, right? That would be we would have to move the decimal place 1, 2, 3 places. So 0.02540 liters, right, times 0.100 moles per liter to get the moles, right? We can multiply the volume times the concentration to get the moles, right? And so that's going to give us 0.00254 moles of OH minus. But we know that for a titration, the moles of OH minus has to equal the moles of H plus. So that means that there's also 0.00254 mole of H plus. And so if we want the concentration, cool, we just do the moles divided by the volume, right? That's the equation for concentration, is moles divided by volume. We would have to put the volume in liters if we want a concentration that's molarity. So again, I would have to move my decimal point over 3 times and divide this by 0.02500 liters, right? When I do that, I'm going to get So 0.00254 divided by 0.0250 is going to give me 0.102 molar. So I've got an acid solution that's got a concentration of 0.102 molar. And we can kind of check if that makes sense, right? We've reacted, the amount of acid and base we've reacted is pretty close. So it makes sense that the concentrations should be pretty darn close as well, right? All right, so we did this nice calculation. It turns out that every titration, you're gonna do basically exactly the same calculation. And so we can actually summarize this in an equation that we can then just use over and over again. Right, so what we did is we said the moles were equal to the moles. The moles of H plus equaled the moles of OH minus. To get the moles of OH minus, we multiplied the volume times the molarity, right? And so instead of saying, okay, moles of H plus equals moles of OH minus, we can say, okay, well, the moles of OH minus is just the molarity of the OH minus, the molarity of the base, times the volume of the base, right? This 0.0254 liters times the 0.1 moles per liter. And then moles of acid is also just going to be the molarity of the acid times the volume of the acid. So a simpler way to do the calculation is to use this formula. This is exactly the same work that we just did up here. It's just condensed into an easier to use formula. In particular, one nice thing about this formula is if you're doing all the work and actually calculating the moles of OH minus and the moles of H plus, you have to convert from milliliters to liters, right? Because molarity is moles per liter. But as long as you're using this equation, you can actually use the volume in milliliters as long as it's in milliliters on both sides, right? You just need to have the same unit on both sides of your equation in order for it to cancel out. Because essentially, you would be dividing both sides of the equation by a factor of 1,000, and so that has no effect on the overall equation. So let's look at how we would do this calculation for the data that we just got. Right, so we know the volume of the acid was 25.00 milliliters, but we don't know the molarity of the acid. Right, so you can write X, or you can just leave the variable as MA. Right, that's going to equal the molarity of the base, right, which we do know that was the 0.100 molar, times the volume of the base, which was 25.40 milliliters. And so then what we would do is we want to solve for MA, we want to solve for our unknown, so we would divide both sides of the equation by 25. Right, so we're going to have 0.100 molar times 25.40 milliliters divided by 25.00 milliliters, right? And then you can put that into a calculator, and what you'll get is 0.102, and the milliliters cancels out with the milliliters, so we've got a unit of molar. So you'll get exactly the same concentration that we did using the long way. So I actually definitely recommend using this equation and using this method to figure out the molarity of the unknown. So you plug in everything that's known, and you should have one unknown variable that you can then solve for. Awesome. So this is how you would calculate the concentration of an unknown acid or an unknown base by reacting it with the opposite, right? If it's a base, you react it with an acid. If it's an acid, you react it with a base. This is how we're able to find the concentration of things like lemonade or toothpaste or other everyday objects where we don't create them in a lab, and so we don't have an easy way of knowing the concentration.
All right, I hope that was helpful. For the next couple of lessons, we'll be doing lab activities. So I'll actually see you next week when we start talking about electrochemistry. Bye.